So we'll be recording this session, just be aware. So my name is John Black, and I work in the instrument support for GC and GC instruments, GC mass spec instruments for SCION Instruments. And also joining from SCION Instruments is our new product manager, Evelyn. And from the SCION factory, we have Edwin, our senior production engineer responsible for final testing of the instruments before they're dispatched to customers, and that includes the instruments that we'll see today, the Simdist and DHA analyzers, which will go out pre-tested to our customers. So for the comfort of everyone, you're all on mute, I'm afraid. So for questions, please use the chat box. Edwin and Evelyn will try to answer your questions with a quick reply. Otherwise, we can email afterwards. Okay, so let's begin. So we're going to look at the boiling point distribution of crude oils, and we're looking at gas chromatography methods ASTM D7169 for Simdist, and we're going to combine that with a detailed hydrocarbon analysis ASTM D7900. So we're going to get a combined Simdist from these two GC methods. Okay, so crude oil, that's the sample that we will be analysing. It's the world's most in-demand commodity. You're looking at over 100 million barrels a day are consumed worldwide. USA 20 million, Europe 15 million, China 14, Canada 2.4, 1. So it's an important commodity, a raw material that's used for hydrocarbon fuels, our petrols, our aviation, and also we'll manufacture lubricants, music plastics, industrial chemicals, your detergents, your solvents, these sort of things. So it's a very important material. Here we go. So before we can get our gasoline, our petrol, or diesel, the crude oil is taken to an oil refinery, arriving in ships, super tankers, pipelines, and the refiners will process the oil to produce the petrols, the diesels, the oils. So the first major processing unit on the refinery is the crude oil distillation unit. So in simple terms, the crude oil is piped into a gas oil fired furnace, heated to raise the crude oil to about 400 degrees Celsius, and then it's piped into one of these distillation columns shown here. So these are tall steel structures, easily 50 meters in height, and they've got an arrangement of metal pipes inside. So the distillation column is going to separate out the different components, different cuts of the crude oil. So we've got the light gases at the top, the butanes, the propanes coming out at the top with the lowest boiling point. And then we've got withdrawals further down the distillation column, going from the higher boiling points at the top, and so the ones with the most volatile ones at the top, to the higher boiling point ones at the top, with the asphalts at the bottom. So inside we've got a crude oil that's been vaporized. It's also been mixed with reflux coming down. And then we can, and then we withdraw at the different levels at these pipes, the different components, the gases and naphthas, kerosenes, gas oils, lubricants, fuel oils, and that sort. And they're all being fractionated off depending on their boiling point. It's a fractionation column. So as the fractions go down, we get at the top, you can get our butanes and propanes, as said. Then we can get some naphthas, which can then go on to be for the gasolines, and then we can have our kerosenes and diesels, and some of them will be go off to other refining units, especially the lower ones, the heavier fuel oils and these sort of things will go off to vacuum distillation units, and the others We can go to fluidized catalytic units, cat crackers, hydrocrackers, so that the refiners can upgrade and blend for the gasolines, the petrols, the diesels. So oil is a natural product. It's varied in substance. So here we have in the middle what's called the true boiling point distillation curve for the oil, for a crude oil here. And crude oil has been a natural substance. Different oils will have different distillation curves. So this plots the volume percentage distilled, the component cut points for our naphthas, the kerosenes, light gas oils, heavy gas oils, and the remaining residues. As you can see, this is also like similar to the takeoff points, withdraw points we have here on our distillation column. So the TP curve, distillation curve, is useful for the refinery managers, the engineers, the process operators. It's a very useful assay of the crude oil on the composition. It gives you an insight into the yield and quality of the crude oil. So in the chemistry lab, we could take a sample and we can place it in a distillation flask with a thermometer on the top and heat the flask with the exit of the distilling flask connected to a condenser. We could collect the distillates in a beaker and a measuring cylinder, and as we heat the flask and we measure the temperature and we measure the volume of distillate, we could also create a TB curve. But there are some drawbacks. I mean, automation, precision, reproducibility, the fire hazard, and also limited sample range. I mean, some of these devices will easily use up 100 mils of sample because it's quite a large sample, so it is quite a fire hazard. Just a list of drawbacks. Measurement time is about 60 minutes, but it is quite a large volume. It's 100 mils you're going to need. A lot of, with the safety, you'll find a fire extinguisher beside them, and it can be a manual filling process. There's an operator bias there, and there are also some errors in the volume measurement. Manual cleaning is required. Yeah, the flasks themselves are quite an expensive consumable material. So there is an alternative to this classical laboratory technique by using gas chromatography. SCION has two GC platforms, 436 GC and the 456 GCs. Both GCs can be used in this application for Simdist. The 436 is small and compact GC. It's limited to one detector and two injectors. It's good for cramped labs. It's very compact and for dedicated analysis. Otherwise, we have the larger GC. It can accommodate more detectors and injectors, 3 of each. And also the column oven size is almost twice the depth of the little 436. Both ovens, they can accommodate the 7-inch GC kgs. You use traditional nut and ferrule connectors, so you can use columns from not just from SCION, which we do sell, but other manufacturers sell. So if you've got some old traditional columns that you want to use, they'll fit in both the 436 and the both 456 GC. So it's fully automated. There's high precision, high repeatability, very reliable. It's a lot safer. The small sample volumes are going to be used. We're going to put you could use 2 mil vials. So again, you've gone down from 100 mils to only 2 mil vials. So for GC software, in addition to the hardware, we've got software to operate, control the GC, to acquire the data. We can use the compasses, SCION's Compass CDS to do that. Now, once we've got our data files, we're going to use a plugin to the software, to our software. It's the Eclipse Picture Reporter plugin that we'll use for the Simdist and the DHA analysis. Underneath this is underpinned by a Microsoft SQL server that's running in the background. So for the two samples that we're going to get, we're going to run on one application, the Simdist application, and we're going to run a second sample on another GC to do the DHA analysis that will produce a short Simdist curve that will incorporate into the main Simdist curve you can see here. So the software behind it does this for you. It will work out the Simdist curves and we'll combine them together into one report. This is what the plugin is doing behind Compass. So here we have the plot on the left-hand side. This black chromatogram is the blank subtracted chromatogram for the Simdist sample, and overlay it in this deeper black line is the boiling point distribution curve from the Simdist sample. And to get more accuracy on the lower boiling points, we've run separately a DHA analysis, and from that DHA analysis we've exported out on the blue line is the boiling point curve from the DHA analysis. So from the whole crude oil sample, from the blue through to the black is the whole crude oil distribution, boiling point distribution, going from all the way down from the low boiling point all the way up to over 700 degrees Celsius here, and we're getting a recovery up to over about 95% recovery, as we can see here on the chart. In addition to obviously the chart, the software will produce a PDF report. It can tabularize the results for you. It can do a cut point report or a distribution report for you. And it is a combined report. It might be a bit small to see on your screen, but it lists the calibration file used, the solvent blank that's been used with user response, and it also lists the DHA sample that's been combined in this report. So this report can be given out as a PDF, and it can also be exported as an Excel format. So to run the main Simdist analysis for ASTM D7169, we're going to run a carbon deciphered solvent blank. Crude oil is just a bit too much for to inject neat, so we're going to dilute it down in carbon disulfide. It's about 1%. So we're going to run a carbon dissolving blank. We're also going to need to calibrate the GC. So what we're going to do is we're going to run a calibration mixture, which is a number of straight chain alkanes from C5 up to C100. And we know they're well tabulated is the boiling points of these straight chain paraffins, alkanes. And from the retention time that comes out in the GC, we were able to map the boiling point. Chromatography wise, it's not a case of we want to separate all the peaks. It'd be very difficult for us to do that on the GC, and it's not really required. What we want to do is map the boiling points of the cuts of the fractions using GC. So we're going to run this alkane mixture, and that will allow us to calibrate retention time against boiling point for our sample. Now, not all the sample may elute off the column. Some of them will not, all the crude oils may not elute. So we'll run a FID detector response sample, and that will allow us to get an idea of the recovery of the sample from the GC. We can also run a validation standard. This is very useful. It allows us to validate the software and the hardware, and making sure that we're getting good recoveries, we're getting good consensus values, and it gives us confidence that the instrument is actually performing. And then we can go and run our crude oil samples that have been diluted down into carbon disulfide for the GC analysis. So here's our chromatogram for the solvent blank, the carbon disulfide blank. So I think it's a bit over scale, it's gone over scale for the carbon disulfide solvent at the front, at the very beginning of the chromatogram. And then we have the background signal. This is important, just as important having the solvent at the beginning, is we want to have a good repeatable solvent blank while running this instrument. And we want to have a good bleed profile that's consistent. We want consistency with the blank because we're going to subtract the blank. The blank is important because we're also adding carbon disulfide to the crude oil sample to enable it to be injected into the GC. So if we have a consistent blank, our subtraction signal that will be quite accurate and reproducible for our crude oil samples themselves. So the blank is important for that matter, and it's not just the solvent peak we're interested in, but also the elution of the column bleed at the end as well. We want that to be nice and repeatable. So there's a typical blank from the carbon disulfide solvent. Next, now this is the retention time standard against boiling point calibration. So we've got a wax sample that's been added with some straight chain alkanes, and that allows us, in this example, we've run from C8, the first peak, all the way to the last peak, which is 49 in the list. The table will be a bit small on your screens, but at the bottom is peak at 100, which equates to a boiling point of 720. So these boiling points are in the databases, and they're well documented in literature. And we use them, what we're going to use them to do is to calibrate the software. We will then input the software the retention times. We tell the software the retention times of each of these individual peaks. We mark out and tell the software where C8, C9 and C10 are eluted. And then that will allow it to build up a calibration curve that will then allow us to map across the retention time to a boiling point. So here is our calibration curve that we're going to use. This is allow us to map the retention time inside a GC to boiling point. So you can see we go all the way up to 700 degrees Celsius. Its retention time is in about the 30 minutes mark. So it's retention time versus boiling point. So this is the important calibration standard, and this allows us to map the boiling point of the crude oil and get our TB total boiling point curves. Next, we'll run an FID detector response signal. This is really just in cases where the sample will not fully elute from the column, is that we'll be able to monitor the recovery, see what the recovery of the sample would have been. Now for this, we're going to use the reference oil 5010 as the response factor for the FID. So that's important to be running this ASTM, maybe a bit different from your other Simdist analysis, but it's included in the 7169 ASTM. Because also we'll use the same oil, and not only to get the FID response, but also we'll use it to validate our analysis, both the hardware and the software. So these in the table here, on the right hand side, we've got a column for the cut point, the initial boiling point to the final boiling point in 10 degrees. And then we have a consensus value for the cut point. So with the initial boiling point has a consensus value from the ASTM standard of 428 degrees Celsius. Our GC analysis calculated the result of the initial boiling point of 426.3 degrees Celsius. And we're allowed an allowable difference of 9 degrees Celsius, so we're well within the allowable difference for the consensus value. And here we have the cut point all the way up and we are in well agreement with the allowable difference for the cut points up into the final boiling point of 655 degrees Celsius, and we have on this GC result we have 648.7. So it gives us good confidence by running these validations, these certified reference materials, that the GCs when they leave the factory and when you use them is fit for purpose and is accurate. So now that we've set up the GC, we've run our blank, because we're going to do a subtraction of the blank. We have run our straight chain in alkane mixture all the way up to C100 to map the boiling points. We've got a response for the FID. We've validated the analysis. We're ready to run our samples. So here's an example of a crude oil sample. It's a lot of light 10s on it, this crude oil sample. So there we have an example. We're not, I mean, what I should emphasize here, we're not, it's not important for us to have complete resolution of the individual peaks of the crude oil. That'd be very, very difficult for us to do. What we're going to do is we're going to take that retention time versus boiling point curve, and we're going to map across the results to produce that distribution curve for the boiling point of the crude oils. So the hardware we've used for this, you could use a 4360 as shown here. You could also use the larger 456 GC if you wanted to put other Simdist columns. But we've got to remember this is quite a high temperature Simdist column that's going to go in this. So this is quite a restriction because you're going to go up to 430 degrees Celsius. So up there, 435 degrees Celsius. So it's really quite high temperature. As you'll see, this is why we cannot fit the DHA in the same GC. We're going to use a different GC just because of the column that we use. So it's a cold on column injector we're using. We're also going to use a high temperature FID. All the ferrules in that are all selected for high temperature work because we need to go to the high temperatures to elute the last bits of the last fractions of the crude oil. We have different cooling options to cool the oven and cool the cold and column injector. So the column we're going to use is really quite a very short one because we're more interested in the distribution, the mapping of the boiling points than we are of physical separation. So it's a short column, only 5 meters long. It's a megabore at 0.53 millimeters ID, and the film thickness is very thin at 0.09 microns film thickness. It's a high temperature Simdist column that we're using. So it's just a very short megabore thin film column that will be used in this analysis. So here's the injector that's used. It's a cold on column injector. There's no split involved. It doesn't have a split line fitted. It's just a very simple capillary on column injector. We're using a megabore column. You can fit 0.32 ID columns. In the cross sections here, we have a cooling pipe, the yellow cooling pipe. Now it can be liquid CO2 or it could be liquid nitrogen, liquid CO2 being the most popular. And it has a heater on the side as well, a heater cartridge that's really sort of inside that silver or sort of grey part at the side. So it's very small and compact. It's got a very short nozzle in the GC column that goes into the GC column area. So there's not a lot of area for cold spots at all. That's why it's very useful in this technique. There's no cold spots really. The glass liner that you see is really a needle guide for the Autosampler syringe needle to go in, and that just guides it onto the top of the column itself. So it's an on-column injector. There's no split, so it's 100% of the sample will go onto the column. We're injecting quite small amounts, so we're going to we can take an ordinary Autosampler syringe. From the Autosampler, it can be all automated, and it will do the on-column injection for you. And you're talking about maybe only injecting 0.2 of a microliter from the 2 ml sample vial. So being an on-column injector, the heater on the side is ramped. So if I go to the next slide, we'll be able to see the temperature program that's used for the injection. So here's some screenshots from our Compass CDS software that's used to control drive the GC. So we're going to start at a warm 70 degrees Celsius. We're using carbon disulfide, it's diluted in carbon sulfide. So we have an initial point of 70 degrees Celsius, and then on injection, we're going to ramp at the same rate as the oven. We're going to follow the oven. And we're going to ramp it all the way up to 430 degrees Celsius, and just hold it there during the analysis. So also with the carrier gas, the control of the carrier gas onto the injector is by an electronic flow controller. It is a flow controller, not a pressure controller that we're using this time. It's an AFC Model 23 flow controller, and that's flowing quite rapidly at 25 mils a minute for this analysis. It is a megabore column, a 0.53 ID column that we're using, so we're using quite a fast flow rate through the injector. And we're also ramping it up as well, following the oven ramp that we'll see shortly. So here's our column oven ramp. So it's subambient. It's cooled. You can use liquid CO2, or you can have your oven fitted with a different valving system for liquid nitrogen. CO2 maybe being the more popular one. So we cool the oven to a subambient minus 20 degrees Celsius, and then on injection we're going to ramp at this rate of 15 degrees Celsius per minute all the way up to a very hot 425 degrees Celsius, and we're going to hold it there for 10 minutes. So the analysis time is about 40 minutes. And it's really quite a high temperature. This is why the DHA column will be fitted in a separate GC. It just can't handle that high temperature at the end. So here's a cross-section of an FID or a FID. So it's a high temperature FID. What we've taken is our standard FID. We've put some high temperature fittings inside it, high temperature ferrules inside it, and added some additional insulation so that we can get a higher maximum temperature out of it of 450 degrees Celsius. It's a flame ionization detector, much like others, that will use a hydrogen flame. So we've got hydrogen flowing in with the air and a makeup gas. And when the sample burns, we'll get some ionization, and we'll measure the signal with the FID. So it's a straightforward FID detection, but with some high temperature fittings and ferrules. So you can see on this slide that we've actually taken the set point for the FID as a way up at 445 degrees Celsius. The data rate doesn't have to be very high for this analysis. 10 Hertz is more than ample for this Simdist analysis. We're looking at cut points of resolution. So the data rate 10 Hertz is more than adequate for this analysis. We're using nitrogen as a makeup gas. You can use helium. Nitrogen is just will give you definitely a bit more signal, a better response than helium. If you don't have nitrogen available, you can use helium, but nitrogen is definitely the one that's going to get the most response. And we add the makeup to just add to the response of the FID. So we've got our makeup gas of nitrogen. Remember, we've still got 25 mils a minute of carrier flow, so that builds up to a total flow into the FID of 35 mils a minute. So the combustion flow for hydrogen uses is 30 mils a minute, and the air is 300 mils a minute. So for the autosampler, we've got two autosamplers. Both the tower is the same in both. You can have two different bases. One base will have a carousel that will accommodate 200 2 ml vials. We have an well, it says Autosampler, it's an auto injector is also called, which you can fit 10 ml, 10 2 ml vials. You can fit 5 ml and 10 ml vials through it. So it's good for process labs, these sort of things. What I would say is the tower moves, and the tower moves in an arc, so it can cover 2 injection ports. But by moving in an arc, the injector, the syringe is not held above the injection port. And this is important because we're going to inject carbon disulfide, which is very volatile. So this means that the tower will move away from the hot injection port after each injection, so into the cooler laboratory air. So your needle and your syringe will be nice and cool for the next injection into the volatile carbon disulfide samples. So that is so there's no modification to these autosamplers. It's the same autosamplers that would go out for any sort of liquid injection. It's just that with it, it's very useful to have that tower to move away from the hot injection port after analysis. We don't have to have any extra cooling. We can cool the vials. There are cooling options for the vials. There's a hot plate as well if you want to sort of slightly heat. But remember, the sample is diluted in carbon disulfide, which is very volatile in itself. So here we have the chromatograms shown in the plugin software, the Simdist DHA plugin software, Eclipse, hydroporter tool. On the top chart, we can see the black line is the chromatogram from the crude oil itself, which will be blank subtracted. And below that, in a sort of pinky color, is our alkane calibration mix. It's going to map across the software. So the software will handle all this for us. And what it will do is it will create the Simdist curve. As we've seen, this is the blue line in the bottom. And actually the black line, you can see we've dropped the baseline a lot on the bottom because that's the correct, we've taken away the carbon disulfide on the bottom plot itself. But for the software itself, it's because it's been pre-calibrated with the pink alkane mixture, it's got the retention times of the alkanes up to C100. It can automatically process the sample and slice it for us and build the boiling point all the way up to, you see here, 730 degrees Celsius. So this is the Simdist, the blue line is the Simdist plot without any DHA analysis added. This is the analysis straight away from the Simdist software plugin. Now, the issue we're going to have with this analysis, especially at the really lower boiling point ranges, is the influence of the carbon disulfide, because it obscures the bottom elution of the really light material in the crude oil sample. There is some quenching factors in the software, but what would be better is for us to run a DHA analysis and add to the very bottom of this curve, which is quite an important area. It's where the naphthas are, so it's really important for us to get them this information. It makes it much more accurate when we combine it, as we'll see. So when we take this, this is for our first sample from the Simdist application, and then what we can do is, if we run our DHA analysis, we get a lot more accuracy. Where the blue line is the start of the distillation, and you can see it's a very steep curve at the start. So being a steep curve is that we would want to make it more accurate, because when we move up the curve, we're moving up boiling point, and it will affect, will improve the accuracy of the recovery, the yields, the information that we have at the bottom range. Because when we get into the Simdist curve, it's much more gentle, it's much more straighter. Whereas in contrast, the curve for the DHA analysis, where even for the Simdist down at the bottom range, is very steep and very quick. So by running the DHA analysis, we get a much more complete and accurate boiling point distribution. So moving on to the DHA analysis, we're going to run the samples under the ASTM method D7900. So again, we're going to run a calibration mixture, only this time from pentane up to C9, nonene, for the straight chain alkanes. And what this time, we're not going to calibrate against boiling point. We will use boiling points in the calculations. It will use that, yes. But first, we're interested in really calibrating it against the COVAX index, because inside the software, there's a big database, and it has a large number of organics, hydrocarbons listed with their COVAX index that we will be able to reach into and find out what compound was eluted at that retention time. So we'll run 2 samples this time, a calibration mixture and a crude oil sample itself this time. But instead of adding carbon sulfide, we're going to add a little amount of an internal standard to be able to do the merge of the DHA analysis. We're going to merge these results with the Simdist results. So there's our calibration mixture from pentane, hexane, heptane, octane up to nonene. Now, by definition, pentane C5, COVAX index 500, hexane C6, 600, C7 700, 8 800, 9. So they, by definition, that's how they are set out for a COVAX in the database. And what we'll do is that when the unknown, or from our DHA analysis, we'll be able to find the retention time, and then from retention time we'll look up the database, and we will be able to infer what that compound is likely to be. The software uses more than just the retention time. It'll use a little bit of information that you do, what's called presets. You can tell if it's more a reformate or what sort of history the sample is, and that will guide the database in a certain way when it looks up the COVAX database, and it will then label the peak for us. So that's the calibration mixture. So that will calibrate the COVAX for us. And then we can run, we're only going to run the front end of the crude oil. We're not going to run the whole crude oil sample, just the front end. You can see we've added 1 hexene as the internal standard. So that there you can see the front end of the crude oil sample. The hardware we're going to use for that for the analysis of the front end as follows. So we've fitted a splitless injector. So unlike the Simdist, which uses a cold on column, we're going to be using the splitless injector this time. Again, detector wise, we're using an FID, but we're going to use a backflush. So we've got 2 columns, a pre-column followed by the main analytical column, and in between we're going to have a additional carrier gas source on a pressure regulator, an electronic pressure regulator, that will allow us to backflush the pre-column, because we're only interested in the up to C9 on the crude oil sample, because we've already got the information from C9 upwards from the Simdist column. For the distribution, it is the very volatile material that we want to get information from the DHA analysis. So again, this can be fitted into a 436 GC if you want something nice and compact and you want high throughput. You can easily fit it in a 436, but we can also fit it into a 456 GC if you wanted to run other DHA analysis as well. So you can see that there's a 436 GC with the capillary column fitted into the oven space, which is just a normal air-cooled fan oven that we have, and it's also fitted with an autosampler on the top for automated injection. So the columns we're going to use, the pre-column is quite a long column. It's 20 meters, it's 0.25 millimeters internal diameter with a 0.25 millimeter micron film thickness. And then for the main analytical column, we've fitted a very long 100 meter DHA 0.25 ID internal diameter with a thicker film, a 0.5 micron film thickness. So that's the setup. We're going to inject onto a splitless injector. We can use helium carrier gas. We've got our pre-column, which we're going to backflush all the heavier material off, because we're going to only put the light materials up to C9 onto the main analytical column. And then we've got a backflush in play so that we can backflush the heavier material back out the splitless injector. So here's the injector itself. This is our standard splitless injector. Well, very much like the cold on column injector, it has a very short nozzle that protrudes into the oven, low dead spots, cold spots into the oven. Now, unlike the cold on column, it's not a programmable heater that's attached to its isothermal. It's quite a large liner volume that's inside this injector, sort of approaches 1 mil maximum is the volume inside. So it's a large volume liner inside, allowing so very capable splitless. What's quite unique about it is it has a split vent line at the top of the injector and also one at the bottom. So that makes the solvent tail for the split and splitless injections very sharp, well defined. So let's look at the parameters that were used for this analysis. So here we have screen grabs from the Compass CDS software that was controlling the GC. So on this one, we're heating up the splitless to 275 degrees Celsius. It's held there for the duration. Splitless does not have a programmable heater on it. It's an isothermal injector. It does have a split. So unlike the cold on column, which there was no split involved, it doesn't have a split line, we're actually going to split this. So in this example, we've employed a 1:100 split ratio. And then for the helium carrier gas that's being used as a carrier gas, we're going to pressure program the carrier gas. And that will allow us to backflush the instrument itself. So initially, we have the pressure on the head of the column or the injector, the inlet, at 53 psi, and it's held there for 45 minutes. And then after 45 minutes, we're going to drop the pressure down to 23 psi, and that will allow us then to backflush the pre-column. So it'll backflush the pre-column out the split line at the split vent after 45 minutes, because we're not interested in the heavy materials, we are only interested in the light materials. As we say, we've already got the information of the heavier materials from the Simdist method. What we want to do is complement. We want really more information, more accuracy at the front end. So we're only doing DHA on the front end of the light materials. So we have incorporated a backflush. This avoids luting all the heavy tarry residues onto the analytical column, which is not required. So here we have in the middle, between the pre-column and analytical column, we have this EFC24 pressure regulator. It's an electronic pressure regulator, and it's got a set point, a static set point of 45 psi. So what we've done is we reduced the pressure on the injector down to backflush the pre-column. So the column oven program is set out here. You can see the screen grab here from the software, from the Compass software. So we're starting at just above ambient at 35 degrees Celsius, and we're holding that for half an hour, 30 minutes. So quite a long hold, so that you get full resolution. And then we're going to ramp it quite slowly, quite gently at 2 degrees Celsius per minute, up to 115 degrees Celsius. And then when it gets to 115 degrees Celsius, we're going to ramp it 10 degrees per minute up to 200 and hold it. So it's quite a long, it's 83.5 minutes long analysis. It's all automated. So there we come to the FID. So it's the identical picture. The difference is we've got no special fittings, no special ferrules, no additional insulation. So it's the same FID, but we've not enhanced it to take the temperature. Its maximum temperature is 400 degrees Celsius. So we're using FID detectors. And again, you can see actually we only really require it to be at 300 degrees Celsius for this analysis. We have increased the data rate up to 20 hertz. Again, we're using a makeup gas. Nitrogen is our favorite. You can use helium. We've turned it up because we're using a lot lower flow, so it's now at 28 mils a minute. But standard, we've got the hydrogen at the same 30 mils a minute and air at 300 mils a minute, as we normally would do. And just like the Simdist GC, we can have got a choice of the same choice of autosamplers that can be used. I'll just skip over that. We've talked about that earlier. So I've two GCs because we've got a Simdist analysis that goes up to over 400 degrees Celsius. It's too hot for the DHA columns. It will degrade them. It will. It's not really good for the film thickness. It'll just degrade too quickly and we'll lose performance. So it's not. We can't really put the DHA columns inside of the Simdist GC. We're going to have to use two GCs for this analysis, but we can use one PC to control the two GCs. So we can use one software package with the two GCs. In this arrangement, we've got a standalone PC here, easily controlling the two GCs, and the data and the reporting will all be done by the plugin itself. So it's quite good actually to really have them attached to the one PC for the data analysis. So here's a screenshot showing the sample setup. Compass itself is used to control our GCs. It's used for the GC control, the data acquisition. It will collect and record the chromatograms, and it's very, very small on the screen, but right at the end is our plugin that we'll be using. It's the one last icon on the second row is the Petra Reporter plugin. So we will export, or we'll call in the plugin to process the data. The plugin has the database, it has all the information. It will take the chromatogram and it will do the post-processing for us. But the starting of your sequences, your acquiring of data, the control of the GC will all be done with Compass. As you can see here, I've got a sequence ready to go for the Simdist GC and another sequence ready to go below it for the DHA analysis. It's the Simdist sequence that's shown here on the right-hand side. It has it's got a sequence of 5 samples to run. I can put the run information, which will be carried through to the Simdist application. So they're going to run for 40 minutes. I'll tell which file it needs to inject for the autosampler. I'm only going to inject about 0.2 of a microliter. That's more than enough sample for the analysis. And then to coordinate, to link to the Simdist software to make it more automated, I can call in variables called preset names. I can add sol being solvent, calibration, a response standard, the sample itself, and at the end I've actually rerun the blank just to see what the blank is like. So there's a normal sequence for the setup of the that will allow us to set up and calibrate the Simdist software, the plugin, and run our crude oil samples. So once I've run the sample through Compass, the plugin will come into play, and using the algorithms that are built in behind the Eclipse petrol reporting tool and the databases behind it, it will be able to report our samples. Both, it will be able to do a Simdist report from the Simdist sample. It can wait, and we can do a DHA analysis. And then what we can do is with the DHA, we can merge the two reports together and get a single combined crude oil distillation, including this from the DHA. It's all handled by the Eclipse software, the plugin itself. Behind it, it's got a Microsoft SQL server, a database behind it that will hold in the retention times, the Kovacs indices, the properties of all the hydrocarbons that will allow it to automate the reporting. So you can see here on the main screen, a screen grab from the Eclipse petrol reporting tool. You have an analysis here on the left-hand side. We have a chromatogram in the middle. This is for the FID response standard, and the validation sample. And in pink, we have overlaid the alkane retention time versus boiling point calibration chromatogram samples. You can see here, and on the right-hand side, we can see the presets and of the sample itself. So that is a screen grab of the Eclipse software itself. Behind it, as I said, there's databases that allows the software to run its algorithms to do the reporting. Here we've got the DHA component editor, so you can actually fine-tune the database as well. You've got full access to it, and you can see here it's got all the hydrocarbons. We're looking at the C8 hydrocarbons here. There's dimethylhexane, I can see here, isoparaffin. So it can do piona analysis. It's got them listed into their groups, whether it's a paraffin, an aromatic, cycloparaffin. And alongside here, it's got its index, its Kovacs index, so that it will already be able to automate calculating the Kovacs index for the unknown peak, and then comparing it with the database to label the peak. We can also gear the algorithm for whether it wants to look biased towards more alkanes. So there are some other presets we can add to the search tools when it's looking up the database. And inside the database, you can see it has the boiling points, it also has specific gravities, a lot more information inside the database itself. So that allows it, the software will then work together, and it will then produce our combined Simdist report, as we can see here. Yes, we can plot chromatograms. We can plot the DHA curve. You can see in blue here on the left-hand side, we've got the Simdist plotted from the DHA analysis, adding to the main Simdist curve, the black line from the Simdist analysis itself. And the chromatogram itself is from the Simdist plot. The software itself will create a distribution report for you, a table. It can also do a table of the cut points for you, and it has other reporting options as well inside it. So that really completes. I'm now sort of come to the end. I'm using up my time now. I see we've got about 5 minutes left. So the hardware of our gas chromatograms, fitting with the right columns, that we can do a combined simulated distillation to D7169, and also taken with the detailed hydrocarbon analysis, the 79, and with some sophisticated software, we can create PDF reports. We can also export to Excel. This is also really set out now in our application note. So there's an application note 88, which is available on the web page. It all sets out what I've just been talking about earlier in this webinar in more detail. If you need to contact us, we're on through. You can use our website at SCIONinstruments.com. So I hope you've enjoyed this hour looking at the boiling point distribution of crude oils. It's giving you a little bit of information between the hardware and the software that we can use gas chromatography to help with the assay of crude oils. So thank you very much. If you've got any more questions, put them in the chat and we'll try and answer them. And I hope you have enjoyed this webinar, and thank you for listening.